Hello, this is Frank with Frank's Beautiful Rocks and Minerals. Continuing on with structural geology, I wish to talk about brittle deformation, selected joint genesis, upload and unroofing regional jointing. Even in a regional event that has a similar orientation, the stresses differ place to place, so the pattern will not be perfectly homogeneous. Cooling Poisson and membrane effects tend to create tensile stress field with sigma 3, the least principal stress, oriented along the horizon. During uplift and unroofing, joints are typically vertical since horizontal tensile stress builds up in these beds. The overburden that is removed is going to reduce the vertical stress acting on those rocks, so cooling and contracting affects jointing. Formations solidify, contract, and shrink horizontally as they get closer to the Earth's surface, but they can't shrink in horizontal direction without encountering resistance from other rock. So the horizontal stress causes jointing. Another effect is the Poisson effect, which we'll discuss in a moment. Why do joints form, such as Griffith cracks? Under what conditions? Uplift and unroofing, sheeting or exfoliation, natural hydraulic fracturing. During uplift and unroofing, there's cooling and contraction, the Poisson effect, and the membrane effect. They all cause horizontal tensile stress, generally jointing. Here's a diagram. Here we see original joint formation. Erosion removes the stress. Formation cools as it resists and contracts, as it rises and contracts. And then the core. Let's talk about the Poisson effect. When the stress of the overburden is removed, the rock wants to expand somewhat. This is an elastic reaction to come back from its shape when it was stressed. The Poisson's effect states that if it expands in one direction, then it will shrink in the other direction. So, if a rock wants to expand vertically, then it will want to shrink horizontally. But it is not allowed to, since it is not contracting from a free surface and there is more horizontal stress built up in the rock. The membrane effect. As rock layers move out from the core, their diameters increase, so they are stretched out horizontally, and a horizontal tensile stress builds up. Tensile stress, a pulling away stress, reduces the confining pressure that is normally keeping the joints from forming. And here's the diagram. Sigma 3 is the least principal stress, down to the core. Vertical joints form in the beds. Sheeting joints and exfoliation. From subparallel to topography surfaces. All typical of non-bedded, non-schistose rocks. So it's seen especially, but not only, in igneous rocks. Tensile joints form parallel to the Earth's surface. They can result from a differential during crystallization and residual and horizontal stresses that surpass that of the overburden and vertical load. Note that here the least principal stress, sigma 3, direction is vertical, sigma 3 being the direction of least compressive force. Tensile sub T, tensile stress. This is a pluton inside of which is incipient exfoliation. Here's the pluton on the Earth's surface, exposed pluton, and we have levels of differential compositional layering. Residual stress can consist of sometimes of differential thermal gradients in pluton and country rock or elastic compression stored in sedimentary clastic rocks like sandstone. Here's a diagram. Sandstone layer with stored elastic strain. We have sheeting joints. Here's the axis, sigma sub 1 of the principal stress, and sigma sub 3 of the least principal stress, acting down in a vertical direction. Sigma 1 is acting in a horizontal direction, pushing the rock together. Sheeting joints and exfoliation typically occur in rock that is not bedded because it is not schistose or thin platy layers. They are seen in igneous rocks that are exposed at the surface, seen also in sandstone that doesn't have schistosity. Schistosity refers to schistose, like schist, a rock in layers. These are tensile joints formed parallel to the earth, or the local topography. Since tensile joints form in the direction of the least principal stress, they occur when the overburden is less than the horizontal stress. Here we have the stronger sigma 3 with sigma 1 aimed downward. This is only when sigma 3 is greater than sigma 1. A backward situation. For example, take our pluton. Water comes in and cements everything together. As this rises to the surface, the reduction in stress causes the pluton particles to want to squeeze out of the cement, and the cement is less interested in keeping the particles. So the cement particles will have a differential rate of decompression. At the surface, this causes residual stress. In igneous rocks, this is affected by the differential thermal gradients, which is between the country rock and the pluton. The extruding magmatic pluton closed at the higher rate than the rock around it. It cools faster and causes a differential stress in the pluton, magma, and the country rock that it cements it to. When these are exposed at the surface, the pluton, which is cemented to the country rock, will want to contract faster than the country rock. This will cause differential residual stress to allow exfoliation that is parallel to the contact of the pluton and the country rock around it. So differential crystallization causes the levels of differential layering. I have a diagram. certain molecules crystallize out of the different orders, causing differential compositional layering and exfoliation jointing as seen here in the green lines. Residual stress can consist sometimes of differential thermal gradients in pluton and country rocks, or elastic compression stored in sedimentary clastic rocks like sandstone. Hydraulic fracturing. Hydraulic fracturing occurs when tensile stress at crack tips exceed compressive stresses due to the burden, and pore pressure exceeds surrounding pore pressure. Hydraulic fracturing joint. Sigma sub T is tensile stress. Sigma sub CP is closing pore pressure. Tensile propagation of hydraulic fracture driven when sigma sub T is greater than sigma sub G and sigma sub P. Hydraulic fractures are often marked by many arrest lines. Of great practical use to economic geologists who may increase the permeability and harvesting potential of a rock by increasing pore pressure and forcing hydraulic fracture. From diagram on one of the previous pages that I showed you, the particles can compress somewhat under water pressure. That can't happen in the crack since it is just water, so there is greater pressure in the crack. These hydraulic fractures are marked by many arrest lines since the pore pressure increases. Here is some propagation. The pressure is alleviated, and as more fluid is injected, it is allowed to propagate again. This initially happens in stages. We can increase pore pressure by injecting more fluid into the rock, but in natural hydraulic fracturing, the same thing happens. This happens when sigma sub T, which is the stress at the tip of the crack, exceeds the compressive stress of the rock's grain and pore pressure sigma sub G, sigma sub P, because both of these stresses contain the closing stresses. How does this happen? Well, the pore pressure in the crack is not greater than the pore pressure in the surrounding pore pressure, and it doesn't have to be for hydraulic fracturing to occur. When more fluid is injected into the formation, the tensile stress is going to increase at a greater rate than the pore pressure which pulls it closed, so it will help the tensile stress exceed the total confining stress. This happens by the pore pressure when it's increased. The sandstones in the rocks are not able to move out of its way, so they undergo some elastic compression, which absorbs some of the pressure being applied. However, in the crack that is trying to propagate, there are no grains underlying the elastic compression, so the pore pressure in a relative way increases, so it is allowed to propagate at the tip. This causes many arrest lines. The pore pressure increases. There is some propagation. The pressure is alleviated, and then as more fluid is injected, it propagates again. This usually happens in stages. In the next lecture, we'll talk about joints and veins, a continued subject.